Welcome to The Explainer. Today, we're diving into a truly fascinating journey. We're looking at how we bridge the massive gap between complex acoustic physics and artificial intelligence to literally give robots the power of hearing. We're going to see exactly how these machines process the auditory world around them. Okay, let's kick this off with a really high-stakes scenario. Picture a collapsed building, and it's pitch black inside. When a robot's vision completely fails, how on earth does it know where to go? How does it actually find a survivor in all that rubble? Well, the answer lies in its ability to listen and, more importantly, to understand the exact physical space that sound is coming from. To unpack that, we're going to break this explainer down into 5 key parts. Part 1, how robots hear the world. 2, the shape of robot ears. 3, classical processing limitations. 4, the deep learning revolution. And finally, Part 5, robots in the real world. So let's start right at the beginning with Section 1, how robots hear the world. We really have to start with the holy grail of this entire technology, which is Sound Source Localization, or SSL for short. This is the absolute core task. It's what adds 3D spatial dimension to a robot's auditory perception. Because without SSL, a robot just hears a random noise. But with SSL, the robot knows the precise direction, the azimuth, the elevation, and sometimes even the exact distance of where that sound is originating from. But as you probably know, sound in the real world is an absolute mess. These robots have to contend with some really tough acoustic realities. Sound waves bounce off walls, creating crazy reverberation and echoes. They diffract, literally bending around obstacles in the room. The speed of the sound even changes based on room temperature, causing refraction. And on top of all that, the signal gets heavily masked by background noise, including, and this is a big one, the loud mechanical motor noise of the robot itself. Talk about a noisy roommate. Moving right along to Section 2, the shape of robot ears. Now, the physical hardware, the actual geometry of the microphone array, completely dictates how well the robot performs. On the left here, we've got a binaural setup. It mimics human ears, which is supernatural for humanoids, but there's a catch. The robot's own solid head causes diffraction, leading to this really annoying front-back ambiguity. Basically, the robot struggles to tell if a sound is coming from directly in front of it or right behind it. Now, contrast that with the spherical array on the right. Distributing microphones all over a sphere gives a drone full 360-degree 3D auditory superpowers, letting it track multiple speakers anywhere in the air. However, sometimes engineers just have to get a little creative. Due to the weird physical constraints of a specific platform, they might distribute microphones across totally arbitrary parts of a humanoid's body, slapping them on the head, the torso, even the limbs. They're essentially turning the entire robot into one giant irregular ear, just to capture acoustic data from every possible angle. Which brings us to Section 3, classical processing limitations. If we look back at early robotic systems, we're talking all the way back to 1989 here, they relied entirely on really strict mathematical rules. Techniques like TDOA measured the incredibly tiny microsecond differences in exactly when a sound wave hit different microphones. Beamforming combined those signals to amplify a desired direction, and subspace methods like music used some seriously complex matrix algebra to isolate the direction of a sound. But here's the kicker, and this is what you really need to take away from this. These analytical methods work beautifully if you put the robot in a completely silent, echo-free anechoic chamber. But in the real world, it's a total nightmare. When faced with diffuse background noise, heavy reverberation, or just sources moving around a room, those elegant mathematical models practically shatter. And that brings us to a massive, game-changing shift in the field. We're looking at a fundamental contrast here, moving away from the rigid, classical signal processing of the past, which totally struggles with noise, to the modern, data-driven experience of deep learning. Deep learning architectures thrive on huge amounts of data, and they inherently learn to just ignore the echoes and the background interference. Let's dive deeper into that in Section 4, the deep learning revolution. Just take a look at the surge in deep learning research, marked by the orange sections on this chart. Before 2015, this approach was virtually non-existent, like nowhere. But as computing power exploded, deep learning surged alongside it, and it now represents a massive chunk of all recent research. These newer models actually implicitly learn to compensate for the exact same acoustic challenges that totally defeated classical math. So what's actually under the hood here? Well, instead of handcrafted equations, engineers are using convolutional neural networks, or CNNs. You can think of it like this. These networks treat audio spectrograms a bit like images, scanning over them to extract spatial features directly.
And because they optimize end-to-end on millions of simulated room sounds, engineers don't need to manually tweak the features anymore.
But sound isn't static, right? Robots physically rotate their heads, and human speakers walk around the room. Sound is inherently temporal. That's why convolutional recurrent neural networks, CRNNs, are uniquely powerful. By adding memory cells into the mix, they track how spatial patterns evolve over time. This allows the robot to seamlessly track a moving sound emitter in real time without losing it. Now, you might be thinking, where do they get all this data for a brand new, custom-built robot? Recording thousands of hours of audio is completely impractical. The clever solution here is transfer learning. Researchers first teach the neural network the general basics of sound localization using massive, already existing datasets. Then they gently fine-tune that pre-trained brain using just a tiny bit of data specific to the actual robot. It is incredibly efficient. All right, let's see how this all comes together in Section 5, Robots in the Real World. We are currently seeing this tech completely change the game in two absolutely critical yet totally different arenas. You've got drones saving lives in disaster zones through search and rescue, and ground robots actively monitoring the health of incredibly complex factory machinery in industrial manufacturing. Picture that search and rescue drone we talked about earlier, a UAV hovering over a massive collapsed building. It has to use its deep learning algorithms and its spherical microphone array to pull off a near impossible task, separating the incredibly faint, desperate whistle of a human survivor from the absolutely deafening, echoing noise of its own spinning propellers and the rubble below. It's literally a lifesaver. Or, totally shifting gears here, literally, picture an autonomous ground robot patrolling a massive, noisy factory floor. It's utilizing SSL, but not to find a person. It's doing predictive maintenance. By pinpointing a weird, anomalous squeal or a faint grinding noise in one highly specific gear amidst the hum of 100 other machines, it can actually flag a major fault before a catastrophic breakdown even happens. Of course, despite all these incredible leaps, the journey definitely isn't over. We've got some roadblocks ahead. The next frontier involves shrinking these massive neural network models down into energy-efficient edge AI, so they don't just instantly drain a mobile robot's battery. Engineers are also building self-calibrating microphone arrays, and they're working tirelessly to close what we call the sim-to-real gap, because ensuring that models trained in perfect virtual simulations actually work in messy physical reality is a huge challenge. And this points us right to the ultimate goal, straight from the research itself. The next big step isn't just knowing where a sound is, it's combining the brilliant spatial awareness of SSL with the semantic intelligence of large language models. This would give robots an advanced understanding of exactly what is actually being said from that specific location in the room. So I want to leave you with this final thought to ponder today. As robotic hearing rapidly evolves from simple classical math to superhuman deep learning, these machines are soon going to be able to map and understand auditory scenes far better than we ever could. When a robot can effortlessly pinpoint and interpret every single whisper in a crowded room, how will that fundamentally redefine the way we interact with the artificial intelligence living right alongside us? Thanks so much for joining us for this explainer, and keep exploring.